Let me start by saying that I come from a fairly different field, different angle from most of you here. So I will not say anything about Planck scale physics or anything like this. In fact, I work on integrable models in the ADS-CFT correspondence. And well, there we're trying to solve a different, or at least get a grasp on a different problem in physics, not quantum gravity, but just understanding any quantum field theory in 4 dimensions at finite coupling, which is also a very big problem in modern theoretical physics. But what I'll talk about today is something that will make contact with a bit of non-commutative field theory, which is hopefully of interest also to theories coming from your angle. Okay, so like I said, I work on integrability in ADS-CFT, and I'm going to connect it somehow to non-commutative field theory. So for those of you who don't know what integrability or integrable models are, I will say a little bit about it, but essentially they're models where you have a lot of symmetry, enough symmetry to basically solve a model exactly, but the symmetries aren't, you know, as like it's not as trivial as a free theory, so you still get something very interesting out of there. ADS-CFT, the ADS-CFT correspondence is of course the correspondence between certain string theories and certain conformal field theories. So this basically states that some conformal field theories can be described by string theory and vice versa. I will say a little bit more about that later. But for me, it's really a tool to try and understand CFT. I don't actually, what I'll be talking about in terms of string theory will just be the theory of a single free string. So that'll just be some two-dimensional quantum field theory. Right, and non-commutative field theory I'll get back to. Okay, so what does the ADS-CFT correspondence state? It says that string theory, well, at least in its simplest form, it says that string theory on ADS 5 times S5, so this is some well-defined framework, is in some sense supposed to be equal to what is known as maximally supersymmetric Yang-Mills theory in 4 dimensions. So this morning we heard Kirill Krasnov say that the nicest QFT we have is Yang-Mills theory. This one is a little bit nicer if you like simple theories. So you add some scalars and some fermions and you get a very, very symmetric theory. Now, this of course, you know, if you want to say two things are equal, you need to understand how to relate quantities on both sides. And well, this was a big part of, you know, of the history of ADS-CFT was developing these things more precisely. I will talk about a case where it's very precise and where we can make very quantitative comparisons and very clear predictions. Of course, in super Yang-Mills, as I will call supersymmetric Yang-Mills theory, we have to deal with, you know, perturbation theory. We're dealing with a quantum field theory. So what does this theory mean non-perturbatively? Similarly, in the string theory side, we have two coupling constants as well. We have the tension of the string itself and the interactions between strings. And so we don't quite know what this means non-perturbatively. And then you can ask, well, you know, why do we know this is true? This has been tested in some sectors, in some ways. What I'll talk about is what in my view is the most precise tests. So what we're going to do is we're going to consider what is known as the planar limit. So in this case, you ignore all interactions between strings in this case, and you just focus on the theory of a single string. So this is just a quantum field theory on a circle, and you have to find, say, its energy spectrum, which is still a very complicated problem because it propagates in a non-trivial background spacetime. And this is supposed to be equal to the planar limit of super Yang-Mills theory. So there, you take the usual 't Hooft limit, where you take the rank of the gauge group SUN in this Yang-Mills theory to infinity in such a way that you keep a finite coupling constant and a sensible theory. So there, we're still dealing with some 4-dimensional gauge theory that we don't know how to solve, that we don't know how to approach non-perturbatively, but actually we can do something there. So for example, what ADS-CFT tells us in this case is that if I compute the energy spectrum of this string, it's supposed to be equal to the spectrum of scaling dimensions. So because it's a conformal field theory, your 2-point functions are determined up to a scaling dimension in super Yang-Mills theory. And then, as I'll come back to later, this string turns out to be integrable, which makes it very simple, even though it's at the same time quite complicated still. And using that integrability, we can do very high precision tests of this correspondence because we can compute this energy spectrum basically non-perturbatively. And then we can perturbatively expand it and compare it to what you can perturbatively compute in this theory and find exact agreement. So you can really do like crazy 5-loop computations in this theory and match it precisely for like basically infinitely many operators with what you get out of string theory. And what's nice about this is that using the string integrability, we can actually do it non-perturbatively. So we actually have a non-perturbative definition of at least some operators and some correlation functions in a 4-dimensional interacting quantum field theory, which is a very, very non-trivial thing to say. Right. Now, ADS 5 times S5 is a symmetric space. This is the most symmetric quantum field theory you can have in 4 dimensions. So, can we do something when we start, giving up some of these restrictions? That was basically a lot of people have started looking for deformations of this correspondence, so deformations of either of these two theories in such a way that you can still use integrability, which I will talk more about in a bit, and still get these powerful results, but without having this manifest supersymmetry, manifest conformal symmetry, all this kind of stuff. Right, so that's what I want to talk about mostly today. I will not talk about how we can use integrability in anything. I'm just going to talk about what integrable deformations of this there are, and how they relate to non-commutative geometry of a type that might be of interest to you. And then, well, hopefully, this should provide us with a better grasp on the field theory, so we can hopefully get some insights, although I wouldn't know what to study there, so that's why maybe I'm also here. Right, so what is an integrable model? Like I said, integrable models have many symmetries. So in classical mechanics, it's very simple. You just need as many conserved charges as half the dimension of your phase space, and then you can solve your model by what's known as quadratures. So finitely many integrals and algebraic operations. Okay. In quantum or in field theory, this means infinitely many symmetries. And for the string that I'm talking about, these infinitely many symmetries they form what's known as a Yangian algebra, and it's based on this superalgebra PSU 2,2/4, which is just the conformal SU 2,2 symmetry of ADS5 or of super Yang-Mills, and the symmetries of the sphere, and then supersymmetrized. Okay. Now, these Yangian algebras, whatever they are, they're a type of Hopf algebra, like Michaela was talking about this morning. They can be quantized. And that's also something Michaela was talking about actually this morning. And, well, I'll tell you a little bit more about what these quantizations are. But so the question I want to address today is, can we deform our model in such ways to realize these deformed symmetry algebras? And what would they represent? And, well, there you can guess what the answer is going to be, but I'm going to get there in a bit. So I'm going to tell you what integrability means for this string. I will define the string as a model first, and then I'll tell you what integrability means there and how we can deform it. And then I will talk about the homogeneous case of these deformations as Drinfeld twists. And well, then I'll tell you something which is actually quite well known, is how to Drinfeld twist, in principle at least, quantum field theories. And then I'm going to say, well, if I can Drinfeld twist both sides of the same thing, then they should still be equal. But of course, that's a bit of a broad conjecture, so I'm going to check it with some examples. Right. Okay, so what makes this string integrable? So what makes ADS 5 times S5 integrable is that it's a symmetric space. So you can view it as as a quotient of Lie groups, where these Lie groups have a Z2 automorphism, which leaves the denominator invariant, and whereby the algebra decomposes in a nice way. So what you do to get a model describing this string, so really it's a QFT in 2 dimensions, tau and sigma, with a sort of worldsheet metric. And then what you do is you take 2 group elements of this SO42 times SO6, you decompose them according to the Z2 automorphism, which I denote by these projectors. And then you just take a trace of the first projection, and this one is automatically projected. You put a string tension in front, and then you really get what you would expect from literally a piece of string propagating in a background space with a certain metric, which is just if you really put in the group elements put in an appropriate parameterization and so on, you really get out the metric of ADS5 times S5 coupled to a piece of string. Okay. So it's integrable. What does that mean? That means that we can represent these equations of motion through what is known as a lax pair, through the zero curvature condition of a lax pair. So we introduce some two-component matrix, L, and you can write the equations of motion of the string in this way, so as the flatness of this L, as long as I introduce this L in this way. Okay? And this L can depend on an extra parameter Z, which is known as a spectral parameter. It's completely independent of the model itself, so it's a completely external variable, and that's where the power lies, because when you have a flat object, you can do parallel transport and stuff like that and get conserved quantities. And if these conserved quantities then are, say, an analytic function of some variable, I can do a power series expansion and get infinitely many of them. So these infinitely many symmetries that you can, or infinitely many conserved quantities that you can get from here, they basically constrain the motion of this string so much that it's exactly solvable, even though it's very complicated in principle. Okay. So then you can ask, well, how can I deform this action in a sensible way while preserving this integrability? So this was done by Del Duque, Magro, and Vicedo in the last 2 years. They said, okay, we take the same action, but instead of putting the identity here, we stick in this operator, 1 over 1 minus some parameter alpha times Rg times this projector. This Rg is just the adjoint action of this group element that you use to construct this A up to some R matrix. And this R matrix is an antisymmetric matrix, which means it's antisymmetric under the trace. And it has to solve what's known as the modified classical Yang-Baxter equation, which means that for any two algebra elements M and N, this equation has to hold. Okay? So then it turns out that if you just, if you work hard, you can explicitly prove that you can still formulate your equations of motion in a way that's compatible with integrability. Then you can ask, what does this mean? And this gets back to what I started with. If you then study the symmetry algebra of this string, you don't get a Yangian, but you get what's known as a quantum group, which is also known as the standard quantization of the Yangian. And then you can ask, well, there's also a class of non-standard ones. So I won't talk more about this particular deformation. I'll take a simpler case. If you want to know more about this, I've also worked on this. You can ask me afterwards. But yeah, what about non-standard ones? So what I can do is, or what was done by Kawaguchi, Matsumoto, and Yoshida, was to realize that you can also make this thing work with a different equation, which is just the homogeneous case of the previous equation. So what's known as the classical Yang-Baxter equation. So this is now just a homogeneous equation for R. Okay. So in this case, what you actually get in terms of your symmetry algebra is not a quantum group, but it's a non-standard quantization known as a Drinfeld twist. For those of you that know what a Drinfeld twist is, I won't explain it in detail. For those of you that don't know, it's some object that modifies the co-algebra structure of a Hopf algebra. In particular, this coproduct that we saw this morning, Michele, gets twisted like this. So in the simplest case, this coproduct was just taking some generator x and just tensoring it with 1 and plus 1 tensor x. So this is just how you would do, say, quantum mechanics, angular momentum on two particle states. Say. This is the simplest case. You can do more complicated things, but I don't need to concern myself with that for this talk. And so what you now do is you take some f, which has to satisfy some constraints, and you put it in here, and basically this f is going to be directly related to this r. Okay? This is due to some theorems by Drinfeld, who said that, these Drinfeld twists, as well-defined deformations of a Hopf algebra, they correspond one-to-one with solutions of the classical Yang-Baxter equation. In particular, if you look at the Drinfeld twist and you expand it in this parameter alpha that I introduced, you get something which I denote little r, which is literally a matrix. And this matrix just is basically the same big R, except that I now introduce it through a trace. Okay. Now, finding general solutions of this classical Yang-Baxter equation is an open problem. No one really knows how to classify them for generic algebra, but I can study any particular solution that I can find. Now, as far as I know, there are two classes of solutions that exist. I don't know if there are any more. I don't know if there's a proof whether there are any more or not. But there's two types. Basically, you take two generators A and B which commute, and this wedge product denotes just the antisymmetric tensor product, then it'll be a solution of the classical-Baxter equation, which is known as abelian. And then there's Jordanian, which is just basically based on an SL2 or a Borel subalgebra. Okay. Now, this structure here, for me, means that if I want to do this for the string, then I can only work with parts of ADS5 because the sphere is has SU4 as its symmetry, and that's not compatible with the structure. But okay, that's it. Uh-huh. Uh-huh. No, they classified our matrices dependent on a spectral parameter with certain regularity conditions. These are constant solutions. And this is not known. I mean, as far as I know. And this is later papers. And yeah. I mean, indeed, if you assume certain conditions and you assume dependence on a parameter, then you can use complex analysis to do nice things. Here, however, you just consider constant solutions and you don't know. Right, now, this class, so these two classes, the abelian ones turn out to be related to well-known things, and I don't want to talk about them today. If you want to, you can ask me afterwards. The Jordanian ones, however, they appear to be new within string theory, within everything here. Okay. So what you can do now is you can take such an R matrix, you can stick it in the action. Then you can expand the action, you can find a background. Then you can ask, okay, is this a sensible background for a string to move in? So that means, does it solve the supergravity equations of motion? Okay. You can also ask, well, if I deform this string, and the string was supposed to be equal to some field theory in 4 dimensions, what should I do to this field theory to still get something equal? So there was one Jordanian deformation which was studied in the literature before, which is based on this R matrix. So D is just a dilatation operator, M is just a Lorentz generator, P is just translation generator. I mean, I have a conformal algebra, so I have a dilatation operator. So what you get, if you stick that in the action, you expand, you get something which is ADS5, but modified a little bit, and just a sphere which remains the same, and you introduce a B field. Now you can then work hard and show that this solves the supergravity equation of motion, so it's apparently a sensible thing to put a string in this background and look at it. No, this really means sticking it in the supergravity equation of motion and finding these 5 form, 3 form, 1 form, and so on that complete it to a full solution of supergravity. And that would mean having fermions in your string. In principle, I can repeat this whole computation, including fermions in my string, but it just becomes technically very, very complicated thing to do. So it's basically easier just to say, okay, I have a set of differential equations that I try to solve. Okay, so this looks to be a sensible string theory type thing. The abelian class that I was talking about is all manifestly sensible. So I'm willing to say, okay, probably they're all sensible in terms of string theory. But then I wanted to say, well, what do they mean in terms of ADS CFT? So, well, of course, I should really prove that all of them solve supergravity, but let me skip over that question. So what is their ADS CFT interpretation? Well, it turns out that this was something well known, but I only learned of it when I started looking at the literature, that it's quite well known how to Drinfeld twist a quantum field theory, at least in principle. I mean, conceptually it's clear what you want to do. Whether you can technically implement it is another question, but okay. Right, so how do you do this? Or what should you expect to come out of this? Let me put it that way. So we had this PSU 224 symmetry, which was in the string theory. Of course, it's also in the dual field theory, so super Yang-Mills theory. There it's just the conformal group on spacetime times the, and then including the supersymmetries and the R symmetry of these supersymmetries, okay? So it's supersymmetry in spacetime. This means that it acts on the fields of super Yang-Mills, so just the scalars, the gauge bosons, and so on, via vector fields. You can take the universal enveloping algebra of these vector fields and turn it into a Hopf algebra, like Michele was doing this morning. He said, just derivatives, well, vector fields are just derivatives. So this Hopf algebra then acts on your algebra of fields or of functions on spacetime. So the relevant part is just that I have a coproduct, which is just a trivial coproduct that Michele was talking about, and I have to introduce a multiplication to get back from a tensor product to what I originally had, my algebra of fields. So it's just, if I take two functions and I want to determine their formal product, I literally take their product, right? And then all this is just a formalization of the product rule we all know. So if I act first with the co-product of a derivative on a product of functions and then formally multiply them, I get this, which is of course nothing but the vector field applied to the product by the product rule, and this is nothing but the vector field applied to the formal product. Okay. Now I said I had a theory that was Drinfeld twisted, so now I want to Drinfeld twist Super-Yang-Mills. So how do we Drinfeld twist this co-product? We put in these f's and these on both sides. We do the adjoint action on the co-product. Well, then it won't act naturally anymore on the algebra of fields, but it'll act naturally on a deformed algebra of fields, where we replace the multiplication by mu composed with f inverse instead of the original multiplication, which was just trivial. Now, you recall that the first order expansion of f was antisymmetric. In general, f is just an asymmetric object. So if I take the multiplication of two functions, it will generically depend on their order. So it's non-commutative. So this leads to non-commutative geometry, or if I do it in the supersymmetry part of the thing, it leads to non-commutative supergeometry, but that doesn't really matter for me today. So in general, I would say, well, since I know how to Drinfeld twist both sides of the same thing, or the same thing twice in two different ways, they should be dual to each other in the sense of the ADS-CFT correspondence. So the abelian case that I talked about, there's many examples in the literature that were already studied by other means where it works. There are some subtleties which I might come back to at the end, but let me skip over them. So this Jordanian case was entirely new. It was not known, it was not studied at least, but they should all be non-commutative versions of Super-Yang-Mills. Of course, this is just a bold statement. I mean, I'm just saying I can do the same thing to two objects which are the same in some sense. So, I wanted to test it, and I did so by doing what's known as a brain construction for one of these, or for two of these examples. So, let me now say something about that. So, normally the way the ADS-CFT correspondence was really conjectured was to say, okay, we take a look at some objects in string theory known as D3 branes, and we stick a lot of them on top of each other in flat space. And then if you look at string theory there, you can have open strings, so just pieces of string connecting these D3 branes, or you can have open closed strings, so circles floating around there. And then you can take a low energy limit of this theory in two different ways. You can look at the low energy effective action on these branes from an open string perspective, and then you get really a low energy effective field theory, which is Super-Yang-Mills theory, plus some other stuff. And you can look at, similarly, you can look at a different way. You can look at this completely geometrically, like gravitationally, and then this starts looking like a black brane, so there's a horizon, and you can take a near horizon limit, and then you will see only closed strings propagating in this geometry, and that geometry is exactly ADS5 times S5. And then you have some extra stuff. And it turns out that this extra stuff is the same in both sides. So, and since you're considering the same low energy limit, people say, well, that's a good indication that these two things should be the same thing. Of course, then, since it's a conjecture, it's not a proof, people have been testing it, and like I said, it can be tested very well, but okay. So then I said, well, what I did is I took this and I deformed it in a certain way, and then I showed that it's a Drinfeld twist. Here, I know that I can Drinfeld twist, and I expect some non-commutative Super-Yang-Mills. And I would like them to still be equivalent. Then the question is, are they? And then, well, it turns out that people know how to get non-commutative field theory out of string theory. And, yeah? Uh-huh. Yes. How it works. Well, the same algebraic structure is present on both sides. That's true, first of all, and secondly, this ADS-CFT correspondence is very mysterious in general. I mean, what I'm saying is that I have a two-dimensional quantum field theory of a single string that is somehow equivalent to a four-dimensional quantum field theory. This is also like something crazy, but it works. I can't tell you why it works, but it works. Yeah. Yes. No, it should be. Yes, that might be true. Yes. Yes. So I mean, but then I mean, so you can either say, okay, this might be doable, in which case maybe it's interesting to look at it. In another case, if you don't know, if you were not to know how to formulate such a theory, the fact that I have something which should be equivalent, which is something you can study, might actually help you gain insights into how this should work. But okay. So what I wanted to say is, there's a way to get non-commutative field theories out of string theory, which is to not put these three branes in flat space, but to put them into some curved space in general, with some magnetic field. Okay. And what I then wanted to say, what I then wanted to do is basically find such a space, such that if I look at the literature on non-commutative field theory, I really predict this, what I would find by a Drinfeld twist. And on the other hand, if I look at this other low energy limit, I really get this deformation of ADS5 times S5 that I found. So I did this, I concretely checked it for these two cases. So this was the case I showed you before. This is a slight modification of this case, which is more generic. If you really look at the detailed calculations, I can't use all sorts of tricks that work in the first case. Also, this case still has supersymmetry, this case has none. So the fact that it works in those cases is actually kind of nice. So what you get, if you really put in the Drinfeld twist, or just look at the brane geometry, you get a non-commutativity of this type. So you have a light cone coordinate not commuting with the, let's say, the two transverse spatial components. Okay, so this is some example. But now we can reverse the logic. Now that I've checked it and I'm fairly confident that it works, is say, okay, if I have some non-commutativity that I like, which you can realize by a Drinfeld twist, then I can take the corresponding R matrix, I can stick it in my string action, and I can find the background that should in principle be the string jewel of it. Okay, so that I wanted to then do for, say, Kappa-Minkowski space, which we heard a little bit about this morning. So this has been studied extensively here as a space on which the Kappa-Poincare group naturally acts. What I'll talk about is not Kappa-Poincare group, because Kappa-Poincare group is not a Drinfeld twist. That's a proper quantum group. But okay, it still looks the same. So what I did is I took this R matrix, so just put some parameter in front kappa inverse, and then take the dilatation operator wedge one momentum in some direction. Then you get a non-commutative structure, which looks like this. So the mu here is the same, and then any other coordinate commutes to itself. So this is a Kappa-Minkowski space. As I said, it's a module for twisted algebra, not for Kappa-Poincare. But it's been studied extensively in the literature as well. So now I put this R matrix in the string action, and I get, well, what I would think is a conjecture for a gravity jewel. So this thing, like I said, there might be some subtleties with my conjecture, which I didn't address yet. Basically, I expect them to be related to the fact that, to the case where these backgrounds come out singular. Because this singularity might indicate that at some point in your space-time, basically you get uncontrolled string production, so the limits that I'm taking no longer work out. But in a case where there's no singularities, I expect it to work out fully. And so this I can do for the case where this is a space-like translation or momentum. And then you get this deformation of ADS5, where I had to introduce some hyperbolic coordinates to make it presentable. But so in principle, this is some gravitational background for strings or supergravity, through which we can try to describe, well, what happens if you Drinfeld twist super Yang-Mills in such a way that you get Kappa-Minkowski space on which it's defined. And so in principle, by studying, say, classical gravity in this space, we can study strong coupling behavior of this super Yang-Mills. And by integrability, we can actually do better than that. Yeah. Yes. Yes. No, they're definitely not identical, but yeah. Now, of course, like I said, I mean, I should really check that it's a solution of supergravity, which I'm trying to do right now. I should check that I can really find these three branes in some deformed geometry that give this, like in the other examples that I did. I'm also trying to do this now. I would also like to understand whether singular cases might actually be okay, because I would find it a little bit surprising that it works in one case but not in other cases, but okay. Right, so I still actually have some time left, but okay. What have I told you today? So I tried to show you what so-called Yang-Baxter deformations of the string are. So they're just integrable deformations of the string in a well-defined way, of the string sigma model. I focused on the homogeneous case, and I argued that they're Drinfeld twists. And then I said, well, okay, we can Drinfeld twist the dual field theory the same way. So they should be dual. So this gives an ADS-CFT interpretation for this new class of integrable string models. And the fact that they're integrable makes it very powerful. I'll say a little bit more in a second. So basically the upshot is, if you have a twist-type non-commutative structure, then I can conjecture a gravity dual for super Yang-Mills on that non-commutative space. Okay, so I gave an example of Kappa-Minkowski space. Now there are many open questions. So like I said, there's questions whether they're all sensible string theories. Then there's a question whether this deformation is really a solution generating technique in terms of supergravity. If it takes a solution of supergravity equation of motion to solution of supergravity equation of motion manifestly. Like I said, I wanted to find a brain picture. Now, we heard this morning a bit about Kappa-Poincare, right? This Kappa-Poincare group is a quantum group derived as a contraction limit of SOQ32. The model I started with, this quantum group model, has PSUQ224. So maybe we can take a similar interesting limit there and get something interesting. Right. Now I want to understand precisely when this correspondence that I conjectured holds, because there are certain specific cases where it doesn't work, even though it works in the majority of the cases. And I would like to have a classification of all possible deformations of ADS5 times S5. Then, since I have a superalgebra, I can also do this game with fermionic R matrices, which I didn't do yet, but in principle it should be interesting. And then I said at the start, integrability is very powerful. I started a bit by advertising how we can do non-perturbative Q of T. We should be able to do the same here. However, I wouldn't know what to compare to because it's complicated to construct these theories and work with them. Also, I wouldn't know what would be interesting to compute. And finally, there are some subtleties in using integrability in these cases because this twist interferes a bit with some standard tricks that we use. But that should be possible to overcome. So I think that's all I had to say. Thank you.
Thanks for questions.
So before trying with Kappa-Minkowski, I guess people have done that, checking with this theta non-commutativity for Minkowski space,
so
right?
that's
that
the abelian case.
You can obtain it via twist. So what's the picture there? What happens to this these questions that you're addressing for Kappa-Minkowski?
What do you mean not Kappa? So you mean
so in the case of theta non-commutative?
You mean like x2, x3 equals theta, say?
Right.
Right. Okay. So this is a simple case where you take P2 wedge P3. And this gives actually a well-known string background which was studied by Modesena and Russo, which they already conjectured to be the gravity dual of super Yang-Mills on non-commutative space for another reason, but it gives the same background, so that works out. What's interesting here is that if you now consider x0 with x3 is theta, then you start doing stranger things and the string picture starts breaking down a bit. If you then do this brain construction, what you realize is if you take the limit, if you try to take the low energy limit, you actually end up with open string theory in 4 dimensions instead of a field theory. So this is this is one of those subtle cases that I mentioned, and maybe that has a relation with why the space-like case of Kappa-Minkowski works and the other cases don't. I don't know.
We can have one more.
Do you think that this this holographic non-commutative connection can be generalized to ABJM or other kind of?
Yes, it can definitely be generalized to ABGM, I think, because that's also an integrable string background, and everything should work the same. It's just different algebras, but the idea should be the same. There's some subtleties because the construction works a bit different, so it's not been worked out, but I see no reason why it shouldn't. And then, yeah, the real question is, of course, whether you can use this to describe, whether you can just use ADS-CFT to rigorously describe any field theory that you want, and that's something that goes way beyond what I'm doing here.
This is connected to my first question, because if you take an n=1 West-Zumino model in a non-commutative geometry, usually 1/2 of the supersymmetric generators are broken. Okay, so my question is, what happened in super Yang-Mills in n=4 in a non-commutative geometry?
Okay.
How much generators?
Okay, so
if you have the answer.
Yeah, I have some answer. So. Okay, good. So if you take super Yang-Mills, normally it has 32 supercharges. If you take an ordinary quantum field theory in 4 dimensions and you take it maximally supersymmetric in 4 dimensions, it would have 16. It gets 32 because of conformal symmetry. Then if you look at this non-commutativity, it already breaks conformal symmetry because it introduces a scale, sort of. And then you end up actually with 16 supersymmetries instead of 32. In a similar way, I can at least ask for the string theory side what the number of supersymmetries is. And for the 2 examples that I gave you, the first one has 16, the second one has 0. And I expect that to hold also in the dual field theory.
So it's not dramatic from the point of view of calculation, because it's just n=2, like an n=2 supersymmetry. Maybe.
Yes, at least for some cases.
It's more complicated, but
yes.
not obvious.
For some cases. Some cases are also probably more complicated. Yeah. And then, of course, I have to study it at the quantum level, and there it gets more complicated. All right.
Very, very quick.
I think as far as the deformations are concerned, then besides, for example, Jordanian deformations are also so-called generalized Jordanian deformations. So, I mean, there is a quite large list.
For sure.
But I find that I think this, because what is your technique? You are having a flat space as a target space for the sigma model, yeah? Or what is the target space of your Poisson model?
We start with ADS 5 times S5, and then we modify the Poisson model, and then from there find out what the background is actually. Because we modify it on abstract grounds, so we don't see what background we put in until we evaluate it.
No, okay, but you calculate some metric finally.
I gave you 2 metrics.
Before the formations, you have to introduce into the sigma model in order to write the action, yeah?
Well,
because this is the metric in target space, yeah. On this, in the sigma model.
So what we do is we write a.
No, because I don't want to speak too long. I'm saying that of course gravity has much richer family of solutions that you get from these R matrices, because
of course
they are so.
Yes, for sure. This is just a well-defined class. This is a class where you can really constructively do something. In other cases, you would have to study it from first principles. So this is just a shortcut for a particular class of theory.
Last thing, this R matrices involving fermionic generalization. Of course, there are R matrices deforming superalgebras. So there are. I mean, there is no need of question mark. Question mark. You say we should use just R matrices for superalgebras here.
What? Where? You mean the? Yeah, but it's just a question what effect that would have for string theory, not whether they exist or something like this. I just mean, I know they exist, but what is their effect for strings and for the field theory?